Okay, welcome to 2.5. Today we start with a warm-up. Don't forget to pause the video at any time and copy the question down, and then give this one a shot on your own before you restart the video. So part A says to state h at x, and h at x is equal to f composed of g of x. So I can rewrite this saying that f is composed with g of x, and that means I'm going to put g at x inside of f at x. So I'm going to take g at x, 2x minus 5, and put it in for all of the x's in my f at x function. So that becomes 2 at x minus 5 to the power of 4. So we have seen questions like this before where you have to take the derivative of a power of another function. But I can think of this as an outside function, x to the power of 4, and an inside function, 2x minus 5. Later on, on the next page, we're going to talk about, because the g at x function is inside, I'm going to think of the g at x as the baby, and it's inside like a pregnant mom. I know it sounds crazy. And so here I've got the mom function is the x to the power of 4, and the baby's inside of the mom, so she's pregnant. So in part B, it says find the derivative of h at x. And so what we do is we take the derivative of that outside function first. Take the derivative of the power of 4 first. That's taking the derivative of the mom. So when I do that, I bring the 4 down, and then I know I subtract 1 from the exponent. That's just my power rule. So that's how I would take the derivative of x to the power of 4, the mother. So I take the derivative of the mother, and I leave the baby inside. And then afterwards, I take the derivative of the baby. So I take the derivative of g at x, and the derivative of 2x minus 5 is just 2. So here I've got the derivative of the mother with the baby inside, and here I've got the derivative of the baby. I know, it sounds nuts. All right, moving on to our lessons. You can see here I found a comic on the internet. I'm not the only crazy person. It says here they've drawn a picture of a pregnant woman, and they're doing the derivative, d dx, of the pregnant woman. And it says to differentiate the mother and leave the baby inside. So I'm taking the derivative and leaving the baby in there. And then finally I differentiate the baby. And it's how this comic artist learned the chain rule. So the chain rule is if I have h at x and it's equal to f composed of g at x, that's the same as saying that h at x is equal to f of g of x. And then to take the derivative of h at x, I take the derivative of the mother. Remember, the mother is f, so I take the derivative of the mother and I leave the baby g inside, and then I take the derivative of the baby. So this one's multiplication. In Leibniz notation, I can rewrite the same thing. In Leibniz notation, I have some y, and it's a function of u, and u is a function of x. So what that means, if y is a function of u, it means I can write y equals, and over here I've got something with u's in it. And then here it says that u is a function of x. That means that I could write u is equal to something with some x's in it. Maybe there's more than one x. So I have these two functions. So if I want to take the derivative of y in terms of x, that's a little bit tricky because my y function only has u's in it. So in order to do that, I take the derivative of y in terms of u, because that I can do. U is actually the variable for the y equation. And I multiply it by the derivative of the baby. The baby is the u, right? It's the variable of the mother. And so I take the derivative of the baby in terms of x, because that's what I was hoping for. All right, we're going to take a look at an example. So here we're differentiating y equals the square root of 2x minus 1. Don't forget that I can rewrite that as 2x minus 1 to the power of a half. So here, the baby on the inside is 2x minus 1, and the mother on the outside is the power function with the exponent 1/2. So I can take the derivative of this function, and we've already been doing this with our power rules, but just remember it's going to become a little bit more complicated when I have some trig functions or exponential functions or logarithmic functions that I'm also taking the derivatives of. So here I'm taking the derivative of the mother first, taking the derivative of the power of a half. I take the half out front, and then I leave the baby inside. That's the 2x minus 1. And then I subtract 1 from my exponent. And then in my second step, I take the derivative of the baby. So the baby is 2x minus 1, and the derivative of that is 2. And then I can simplify this. I've got a half out front times 2 at the end. That's just equal to 1. And then negative exponent tells me to take the 2x minus 1 to the denominator, and the half exponent tells me to change it to a square root. So I could write it up that way, or I could use my Leibniz notation. So this is the same solution. Here what I've got is y is the square root of the baby. So the baby here, I'm just going to call it u, thinking about using my definitions above. So y is a function of u, y is the square root of the baby. And then u, the baby is equal to 2x minus 1. So I'm going to take the derivative of the mother and leave the baby inside, leave the u, and then take the derivative of the baby. So here dy dx is going to be equal to the derivative of y in terms of u, the derivative of the mother with the baby inside, times the derivative of the baby in terms of x, the derivative of u in terms of x. So taking the derivative of the square root of u, I know that that's an exponent of a half, so I bring that out front. And then I've got my u, and taking 1 away from the exponent, I end up with negative a half. And then taking a derivative of the u function in terms of x, moving over here, I'm taking the derivative of 2x minus 1, and I get 2. So now I can simplify this. Again, I have a half at the front times 2 at the end, so that just gives me 1. So I've got 1 over, and then I'm going to bring the u to the half down to the bottom, to the denominator, because of the negative exponent, and the half turns into the square root. So I have 1 over the square root of u. But don't forget that we said up here that u is actually the same as 2x minus 1. So I can substitute that in, and I get 1 over the square root of 2x minus 1. So this seems like a lot more steps right now off to the right. But again, as our equations get more and more complicated, this version sometimes actually does tidy things up for us. So example 2. In this one, we're going to find the equation of the tangent to the curve, y equals, and we've got a rational function inside of a power function of 1/3 there. And I want to find that equation when x is equal to 9. So my y prime, my derivative, because I know that I want the equation of the tangent, I want the slope of the tangent, which is equal to y prime. It's going to be equal to the derivative of the mother. Remember the mother, the outside function, or the woman, right? She's pregnant, so she's outside of the baby. So the outside function is the 1/3. You're going to bring that 1/3 out, wrap it around the old function, or the baby, the inside function, and then finishing up that derivative, I need to subtract 1 from the exponent. So that is the derivative of the outside. That's the derivative of the mother with the baby inside. And then I'm just going to take the derivative of the baby. Remember, the baby is all of that quotient stuff, so x minus 1 over x minus 8. So using my quotient rule from yesterday, I'm going to take the derivative of the top. The derivative of x minus 1 is 1, times the bottom, and then I'm going to subtract the top times the derivative of the bottom, which is also 1, and then I'm going to put that all over the bottom squared. So there we've got it, the derivative of the mother with the baby inside, and then the derivative of the baby. And so we're going to simplify this just a little bit. Again, I don't care to oversimplify this because I know I'm going to substitute in x equals 9. But that second piece, that second fraction looks a little bit messy right now. I think I can make it look a little tidier. And I'm even going to leave the negative exponent. If you wanted to get rid of that negative exponent, you could flip the fraction inside. In the numerator over here, I have x minus 8 minus x plus 1. Remember, I have to distribute that negative into that second bracket. So I end up with negative 7 in the numerator over my x plus 8 squared. So when x is equal to 9, my y prime, I'll just substitute in 9 for all of my x's. Sorry, I made a slip up here. I hope you saw it. I changed the -8 to a +8. I'm not sure why. So I end up with 1/3, and again, the negative exponent tells me to move the 8 to the denominator, and 2/3 tells me to take the cube root and then square it, and then times -7. Now the cube root of 8 is just 2, and then 2 squared is 4. So I end up with 1/3 times 1/4 times -7, or -7/12. So there we've got the slope of the tangent line when x is equal to 9. In order to come up with the equation of the tangent, though, I need a point on that tangent line. So I want to know what is the y value on my curve when x is equal to 9. So when x is equal to 9, we'll find the rest of our point. Y is equal to, and I'm just subbing 9 into my original equation, right? I just want to know the point on the curve. And so here I get the cube root. That's the 1/3 exponent turns into a cube root. And inside there I've just got 8 over 1, or 8, and I know that the cube root of 8 is just 2. So I've got a point at 9, 2, and now I'm going to find the equation of the tangent. So I start with my y equals mx plus b, and I'm subbing in my y value 2, the slope that we found, the x value, and then I'm going to rearrange this to solve for my b. I'm going to reduce 9 over 12, that's the same as 3/4. Just try to make my numbers smaller so I can do a bit of mental math. So I get -21 over 4. And then I'm going to bring that -21 over 4 to the other side. So I get +21 over 24. And making a common denominator, 2 is the same as 8/4. So I can put those together and I get 29 over 4. So there's my b value. Therefore, my equation is y equals, my slope was -7/12, x plus my b value. And then to get rid of the denominators and put it into standard form, I'm going to multiply everything by the lowest common denominator. The lowest common denominator is 12, so I get 12y. When I multiply that fraction by 12, the denominator goes away. And then multiplying this last fraction, 29/4 by 12, that means that I'm going to reduce 2 times 3, and I'll get 87. And then I'll move the x term over to the other side because I need the x coefficient to be positive. Move the 87 over as well because I need it to equal 0. And there we are, that's example 2. All right, 2 more examples to go. Example 3, it says let y equal u cubed. So the mother here is the cubic function in terms of x. So it's just saying, can you rewrite y so it looks like y equals some stuff with x? I know that y is equal to u cubed, but I know that u is the square root of x. So I could leave it like this, or I could rearrange and make this just a power function. So x is the same as, or sorry, y is equal to x to the 3/2. Now if I wanted to find y prime, this is just a simple power function, so I can bring the exponent down and take 1 away from the exponent. Simplifying this, I'd have 3/2 times root x, or 3 root x over 2. You can leave the 3/2 out as a coefficient if you like. Part B says find dy dx using the chain rule. So now I'm not going to substitute in, I'm going to rewrite my chain rule. So I know that dy dx is equal to dy du times du dx. So we're just practicing, making sure that we understand the chain rule. I should get the same answer, right? Because either way I'm finding the derivative of y in terms of x. So the first one, when I'm taking the derivative of y in terms of u, that's saying just go back up to your equation where y equals u cubed and take the derivative of u cubed. So I'm going to bring the 3 out front, and then I've got u to the exponent 2 because I took 1 away from the exponent. I'm going to multiply that by du dx. So I'm going up to where I have u in terms of x, and I'm going to take the derivative of the square root of x. So I bring the exponent out front, and then I subtract 1 from the exponent. Now to clean this up, I'm going to replace the u with u is equal to the square root of x. So I've got everything in terms of x. So I've got 3 times the square root of x squared times 1/2 times the square, x to the negative 1/2. And now I'm just going to clean this up. So I'm going to bring the coefficients out front. 3 times 1/2 is 3/2. The square root of x squared is just an x, and then I can add the exponents because I'm multiplying between powers with the same base. So I have a power of 1 on this first one, right? This would just simplify to x to the power of 1. And I'm just going to add the exponent negative 1/2, and I end up with x to the power of 1/2. There are other ways to simplify that, but I like to use the power rules. And then I can change that to a root, and I end up with the same thing that I did over here. All right, example 4. So I want to find dy dx at x equals 8 if y is equal to du squared minus 5u plus 3. That's the mother with the u, the baby inside. And u is equal to x to the 1/3 minus x. That's the baby. So I'm going to find the derivative, and I'm using my Leibniz notation. So dy dx is equal to the derivative of y in terms of u times the derivative of u in terms of x. So the first thing I'm doing is taking the derivative of y in terms of u. So I just go to my equation where I have y with equal to something with some u's in it. And I just have to take the derivative of this. So bringing down the 2 exponent and multiplying it by the coefficient 2, I get 4u to the power of 1, and then minus 5. I'm going to multiply that whole thing, so I'm going to put it in brackets, times the derivative of u in terms of x. So now I'm going to my equation where I have u written in terms of x, and I'm going to take the derivative of that. So again, I've got the subtraction, the sum difference rule. I can just take the derivative of the first thing. I bring the 1/3 down, x, and then I subtract 1 from my exponent. And then minus, over here, I'm going to bring that exponent of 1 out front, and I get 1. And then I end up with 1 times x to the power of 0, so that's just 1. Again, I'm multiplying by that whole thing, so I'm going to wrap brackets around that. Now at this point, I want to get rid of that u, so I have everything in terms of x. So I'm going to replace that u with my equation for u. So I get 4 times x to the 1/3 minus 4 times x. I just took the 4 and expanded it into both of these terms as I substituted it in. Now you can continue to try to simplify this, but remember that I wanted to find the derivative at a certain value of x. So I can just substitute in my x value of 8. So when x equals 8, dy dx will be equal to. If you want, you can change these fractional exponents to roots, but you don't have to. Again, I'm going to change that negative exponent. I'm going to move it down to the denominator, and then I'll change, just because I can take the cube root of 8 in my head, so I find that much easier to change it to a cube root. Remember that the cube root of 8 is just 2. So I'm left with 4 times 2, or 8. And then over here in the denominator, I've got the cube root of 8, that's 2. And then 2 squared, that's 4, and 4 times 3 is 12. In the first bracket here, I've got negative 29, and in the second bracket, if I take 1/12 and I subtract 12/12, I'll get negative 11/12. And then if I multiply those numerators, I get 319 over 12. So that tells me that at x equals 8, the derivative of y in terms of x would be 319 twelfths. All right, one more slide. This is your homework. I hope you guys have a good day, and I will see you tomorrow.